All right, let's talk about the definite integral. All right, so now we're going to start defining an integral. So let f be a function from a to b, and we're going to call it the definite integral. Definite integral means it has points you evaluate at. An indefinite integral will just look like an s without this. Notice that this symbol here, the integral symbol, is just an elongated s. So if I took s and kind of stretched it out, it turns into that. Okay. So that's where the integral symbol comes from. So this is just a really long S. And I'm writing the wrong there. Okay. So we're going to look at the definite integral. So it's going from A to B. And we're going to say the limit as of the max. And so your book defines it this way. So the max of the delta x's. So it's just going to be the sum of the function value times that. And so as long as the max one, so we're going to take the limit as the max change in deck. So here I could have a very long one and a short one. The long one as I do my triangles when I'm estimating my function, right? I have a real short one, and a very long one for all the thin cares, right? And we're going to take the max of those, go to 0. So it really doesn't matter. Sometimes in analysis, in advanced mathematics, you'll care to do something like this. 90% of the time, you're going to keep this pretty consistent, and you're just going to say how many intervals we break it in. So this is more like we did last time. So remember, this was just our area, right? Our area underneath the curve from last time was from this definition, right? We're just going to take our delta x's and take the limit as I take an infinite sum of infinitely small x's, right? Where delta x is b over a minus n, and here I'm just choosing this is a right sum. This is, in this case, we're doing our infinity, basically, right? We're choosing r equals infinity, right? So then approaches infinity. That's what we're doing. And these are known as Riemann sums, just where it comes from, because that's the guy who started doing all this. One thing just to make a note of, right? And so here, as long as the function's continuous between a and b, as long as f is continuous, or it only has finite numbers of jump discontinuities, then it's integrable on from a to b. And so as long as it's well behaved, and this is to break a finite number of a jump, I mean, it could be awful, but it's still be integrable. So anything you can think of, I can almost guarantee is integrable, as long as it doesn't explode. And what I mean by that is sometimes there's just too much jumble in there. But for you guys, almost everything's going to be integrable. And so here we're going to just start expressing some of these sums as integration. So here we want to go from 0 to infinity. Okay, so that's what we're going to try to do here. So let's go ahead and express that. I write infinity. Let's not do an infinite integral yet. Let's just have it to pi. Okay. Let's not do infinity yet. Like I said, that's where other stuff can go wrong. And so what we have here is if this is the limit of this, and I just want to write in this, all I'm going to do is go from 0 to pi, because that's where the integral is on, right? And then here I'll have x cubed plus x sine dx, okay? And so dx is what this really represents is an infinite. So basically this is my function value, right? And this is some infinitesimally small amount of x. So we're taking this delta x, we're switching to 0, so we represent that as a tiny d in x, so infinitesimally small amount of x. And I'll show you how to do this. Basically, you just take the antiderivative of this, evaluate it at pi and evaluate at 0, but we do that, and we don't do that until 5.3. Okay, and so that's how you just write all of these out as solutions. Okay. All right, that's it. I don't know why I left the whole page for that. I really don't. All right, so here we're going to do this again. All right, so we're going to evaluate a Riemann sum. So we're going to do a Riemann sum, or basically integral, by taking sample points. So sample to be right endpoints. So make sure to figure out when you're doing this homework and the online stuff. Make sure to know if they want the right endpoints, the left endpoints, the midpoints, or whatever, from 0 to 3, and we're going to choose n equal this. Right? So we want to evaluate this, but we're not going to we're just going to do a Riemann sum instead of the actual integration. Okay. Oh no, we're going to do a Riemann sum and then do the actual integration. So let's start with A. I'm going to leave A over here. Do B over here. I have room to do it all. And we'll end on this page. All right, so here we're going to do a right. I'm doing right, and so here let me just kind of draw this in. I'll just draw a quick picture for you guys. So it's going to start at 0. It's going to be negative, 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 negative. It's going to pop up here at somewhere around 3. So just do right triangles right here. So they're at the right, and we're going to do 6 of them. 1, 2, 3, 4, 5, and then 6. So it looks something like that. 1, 2, 3, 4. Oh, 5, and then 6. Sorry, I could count. Okay. And notice here that all these triangles will count negatively, or all these rectangles will count negatively, and these will count positively. Okay. So we'll have this one, this one, this one, this one, this one, and this one. Okay. So how are we going to do this? So R6. So what's our delta x in this case? Our delta x is between 3 minus 0 divided by 6. So our delta x here is also half, which is pretty standard. So here we're going to type in, so here we're going to have the function value of f of 0.5 times a half plus f of 1 times a half plus f of 2 times a half. Oops, I got ahead of myself. 1.5 a half should be a half plus f of 2 and a half plus 2.5 and a half plus f of 3 and a half. Does everyone see why I'm choosing 0.51, 1.52, 2.5, and 3? Because I want to choose, so I'm going to walk my distance, choose the right point, and so that's my function value times a half. I'm going to walk my distance, so here it's a half again, so I'm going to go up by a half. Here, I'm going to walk my distance, which is a half. That's my new point, and times a half. I'm going to walk my distance, which is a half here. My right point times a half, and walk my distance, and walk my distance. Okay. I can roughly calculate this, and if I roughly calculate this, that's going to roughly equal, you just have to crunch it through a calculator, minus 3.9675. Okay. All right, so let's actually evaluate the integral with what we know how to do right now. And this is the last time we'll do it this way, except for you guys will do it on the homework. So this is going to equal to the limit as n approaches infinity of the summation of I equals to 1 to n of our delta x. So the f xi times delta x. Okay. So delta x in this case is going to be 3 over n, right? So 3 over n. So let's go ahead and pull that out. So this delta x, this is 3 over n, and that's because if I'm going to go, so this will be 3, and then how many times are divided by? We're going to send that to infinity, but we're not going to plug in infinity. We're going to plug in n first. What's our function here? Well, it's right here. So let's go ahead and plug all this in. So here would be the limit as n approaches infinity of the summation of I equal to 1 to n. I'll go ahead and pull the 3n out. We know it's everywhere. And then here would be 3i over n squared. So my step size over n, oh, no, probably cubed minus 6 over 6 times 3i. So that'd be what I'll be plugging in over n. And notice, how do I get this? I just take my step size here and I'm going to add an I to it. And that'll be what I plug in, because every time I'm going to walk, I walk my step size, right? And so if I'm my second iteration, I'll be in the second one, so third. So here I'm walking my step size. Hopefully that makes sense. All right. Then you do a lot. So from here, we're going to take the limit. All right, so now I'll just go ahead and pump this through and pull out what I can. Just for brevity's sake, go ahead and skip the rest of this. It's in the book if you really want to. So just skip the rest of this so we can finish this page. And we're actually going to calculate this through a lot of really fancy series information. Do this. So it's in the book. I probably won't give something like this on the exam. I'm just going to put it out there. You'll do a couple homework problems for it, but you will not do it on the exam. Okay. All right. So I want to finish this last little page. And so it says evaluating this by just interpreting the areas. Okay. And so let me just kind of explain. Sometimes you don't need to do all this fancy math. So what is this? So here I have this. And it's from 1, this is 1, this is 0. So this is my function. Y equals the square root of 1 plus, oops, I forgot a square on that. I should have a square right here. 1 plus x squared, or 1 minus, I'm still on the wrong layer. Minus x squared. But notice this is the same thing as x squared plus y, oops, y squared plus x squared equal to 1. So this is just the fourth of circle. So in order to evaluate a, all I have to know is what a fourth of a circle with a radius of 1, right? And so this would just be 1/4 pi r squared in this case, so just be 1 squared. So this is just pi over 4. So, and this is, we do this in advanced mathematics all the time. It's like, I need to take an integral. What's the integral mean? Find the area. Well, can I just reason through it? And the answer here is yes, right? I can just reason through this one. And here, I just know that this integral will evaluate to be pi over 4. Here, we can do this again, and we'll end on this note. I'm going to start at 0, and I'm going to end up at 3. And here, and this is function y, this is y equals x minus 1. So can I reason what this is without having to break it up? And yeah, in this case here, I'll have this tiny little triangle here, which is one distance over here, one distance down here, which is negative. And so this area here would be 1 divided by half. So this would be minus 1/2, right? For this one. And this will be from 1 to 3. So this is a distance of 2. This height here is 2. So this is 2 times 2. And it'll be half of that. So it'll be plus 2 times 2, which would be 4. But half would be half. And so this ends up being 3 halves to get this here. So here I'll just take this triangle minus half. And so sometimes you can just, by interpreting each of the areas, terms and areas. And so if you just figure out what the area is, sometimes it's just easier just to mathematically solve a puzzle. Okay? Here, any Riemann sum approximation, any Riemann is an approximation of the interval, but if we use the midpoint and regular partitions, we get something that's often better than others, but not always, right? We call this the midpoint rule. So that means just choose the midpoint. So we're going to use this to approximate. We're going to let n equal 5 to approximate from 1 to 2 or 1 over x. Okay? And so to do that, is going to roughly equal delta x, which we need to calculate. So let's do that. Let me calculate delta x real quick. So it'll be 2 minus 1 over 5. So that's our delta x. So 2 minus 1 over 5 is just a bit, right? And then here we're going to use the midpoint rule. And so let me kind of just sketch this real quick so we know what's going on. So here we're between 1 and 2. And so we're going to split it up into 5 equal parts. 1, 2, 3, 4, 5. Imagine they're equal. So this would be 1.2. This would be 2.4. This would be 1. 1.4, 1.6, and 1.8. Right? Would be our partitions here. So from here to here to here to here. We're going to choose the midpoint in between these. So something a little above, something a little below. So that would occur at 1.1. This one would occur at 1.3. This would occur at 1.5. And so here we're going to have the function value at 1.1 plus the function value at 1.3 plus the function value at 1.5 plus the function value at 1.7 plus the function value at 1.9. So this would be 1.7, this would be 1.9. So this is how we've been doing it. So we've been making these. So let's plug in those values. So it'll be 1/5 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7. And did you notice the homework for these two sections when you're doing the midpoint rule or anything? It is worth 6 points instead of the normal 2 points per problem, just because, let's face it, this takes a while to crunch through, right? And if you roughly check this through a calculator, you're going to get 0.691908. Okay. I don't know why I left a whole page for that, but that's it for this page. We'll go to this next page in a second. So go ahead and copy that down. Apparently I should have got more water before starting. Review the graph. Sure, I can review the graph. I'm going to draw the graph a little bit bigger right here so you guys are copying stuff down. So this is 0. We're going from 1 to 2. So the integral's from 1 to 2. And so we're going to break it up into 5 equal partitions. So 1, 2, 3, 4. So that's 5 equal. And each right here is a delta x. This is a delta x. And so forth. And so our distance is 1/5 or 1.2. So here I'll travel 1 delta x, so 0.2. This would be another 0.2. This would be another 0.2. This would be another 0.2. And this would be another 0.2 to 2. So we have 5 equal things. Since we're using the midpoint rule, we're picking the point in the middle as our function value. So this is going to be f of 1.1, which is in between 1 and 1.2. And sometimes it's a little above and sometimes it's far. So for here, I'm going to pick the point 1.3, which is in between 2.1 and 1.2 and 1.4. So this will be f of 1.3 and so forth, right? And then you're just going to fill in each of these little triangles here, or not triangles. Fill in each of these rectangles here, and that'll give our estimate. Okay. And so that's what the midpoint rule does. All right, so let's do the last thing. So here's a bunch of rules for properties of integrals. So if I have from a to b of a function, and if I switch from b to a, and so instead of adding it up positively, I go negatively, right? You just, if you flip your signs, if you flip your a and b, you just negate it. If I find the area underneath a triangle, or a space of 0 distance from like a to a, it's defined to be 0 because your delta x will be 0. Whatever your delta x is 0. So this is 0. If I have a constant, where c is a constant, all right, c is a constant. C is a constant, and I take the integral of that. It's just the integral times the length, right? So if I had something here of like, say it was 5, and I went from 1 to 6, right? It'd be, well, maybe not. Let's just say this was 3 then. This would be 3 times 5, right? So my length here is 5. This is 3, so the area underneath here is 15. So if I have two functions, plus or minus, if I'm plus or minus two functions, I can just split the functions, right? So I can do each term separately if I wanted to. If I have a constant, I can just pull it straight out. What am I doing here? Oh, yes. And so here, another way of doing this is, this might seem strange to do, but it actually has its uses. If I'm going from A to B on some function and I want to figure out what this area is, and if I have some point C, I can do half of it, and then I can do the other half, right? Or a third and the other 2/3, right? This seems weird, but you end up doing this for like stuff like if you have a function, say you have a function, a piecewise function, then it makes a lot of sense to do it this way because you sum it up for one piece, you sum it up for the other piece. Okay. So using properties to evaluate this, we can try to use the properties that we got here to evaluate these. And so let's kind of crunch through it. All right, so here we're going to write this is from 0 to 1, and then I'm going to write 4 dx and then plus 3, 0 to 1, x squared dx. Okay. So what have I used here? I've used this property right here, number 4, to split it apart. And I used number 5 to pull the 3 out from the x squared. Now this we already calculated. We calculated this to be a third. We did this earlier. Or not today, but in the video it looked like we did this earlier. So we did this in example 1 or 2. So this is a third. This is from 0 to 1, so it'll be 4 times 1 minus 0 plus 3. And remember, this was a third. So 3 times a third. If we crunch through all that, this is 4 plus 1. So this all ends up being 5. And then your book likes to ask questions like this. So if I know a function, and the integral of a function between 0 and 10 is 17, and I know, and we have a function, and I know the function between 0 and 8 is 12, what's the function between 8 and 10? Well, zoom out just a teeny bit. So we're going to use this property right here. So from 0 to 10, of f of x equals, let me not be so far out. Let me zoom back in. So from 0 to 10, f of x is equal from 0 to 8, f of x dx, I've got my little dx's on here, plus from 8 to 10, f of x dx. And here I'm just using this property. So here I'm going from 0 to 10. So from 0 to 8 and from 8 to 10 would be the same thing we have here. Now, which one do I know? I know this one. This is 17. I know what this is. This is 12. So that means 8 of 10 of f of x dx is equal to 17. Just move that over. So 17 minus 12. That's just going to equal to 5. Okay. That's it. That's the end of the section. Put a little star right here. Okay, so that's all the end of this one.